Hi everybody. This is the big review for the midterm, and might as well just get started. So let's talk about first. One of the first things we talked about this year is sort of the difference between kinematics and dynamics. And if you remember, kinematics was the study of how things moved, and dynamics, how things move. And the study of dynamics is the study of why things move. And if you can kind of remember, the kinematics, this is all VI, VF, ATD. How fast is an object going? How far does it go? How long does it spend moving? And we usually set up a little chart with that. And dynamics is all about why things move, which we hopefully have realized is basically because of forces and net forces and types of forces. So there you go with that. Please pay no attention to the numbers because they all got wacky. So I'm just going to kind of cruise through this, okay? First question. A stone, it's a one-dimensional question. That's what that 1D is. A stone is dropped into a deep well and is heard hitting the water 4.83 seconds after being dropped. Determine the depth of the well. First thing we should probably do is realize that it is a one-dimensional problem. VI, VF, A, T, D. And if you remember, D is displacement, T is time, A is acceleration, VF is final velocity, and VI is initial velocity. And the one thing that we know, if we're dropping a stone, the initial velocity is going to be 0. So that makes things kind of easy. We know the acceleration is -10 or -9.8 meters per second squared, but I always use -10 when doing calculations just because it's easier to do some things in my head. We're looking for the depth of the well. So that's what we need, and we also are given the time, 4.83 seconds, and I use the equation D equals VIT plus 1/2 AT squared, and it's really just plug and chug. D is what we're looking for, VI is 0 times T, which is still going to be 0, plus 1/2 A is going to be -5. That's why I like using -10, because then 1/2 of -10 is always -5. Times T squared, which is 4.83 squared. And if you do this all nicely out, you should end up with a -116.6 meters. Next, dragster accelerates from rest to a speed of 186 meters per second over a distance of 398 meters. Determine the acceleration of the dragster. Assume uniform acceleration. Same deal, VI, VF, A, T, D. Only this time our acceleration is not -10 because we're not dealing with a projectile. In fact, this is actually what we're looking for. So we're going to accelerate a dragster from rest, so the initial velocity will be 0 to a speed of 186 meters per second. So that's going to be our final velocity, and we got to figure out what the acceleration is to make that happen. Over a course of 398 meters. So we give you 398 and no time, so I don't care about that. An equation that's got a VI, VF, and A and a D would be VF squared equals VI squared plus 2AD. Plug and chug, 186 squared equals 0 squared plus 2A, 398. 186 squared is actually a pretty big number. 34596 equals 2 times 398, which is 796, and I carry down the A. So this times this gives you 796, and 186 squared is 34,596. Divide both sides by 796, and you should end up with acceleration of 43.46 meters per second squared. That's a very fast acceleration. I don't know if that's really a thing, but I pulled some numbers out of thin air, and that's why we end up with this problem. As you'll see with some of these, some of the answers are kind of wacky, and we're more worried about you being able to do the physics, but you should be able to understand that 43 meters per second squared, that's a really quick acceleration. That's like 4 Gs. Jet airplanes do that, not really cars, but they can maybe, I guess. Next, one-dimensional potato gun launches an apple straight up into the air with a hang time of 12 seconds. How high does the apple go? How fast was it going when it came out of the barrel? So again, VI, VF, ATD. We're dealing with a projectile here, so now we know the acceleration is negative 10 meters per second squared. The initial velocity is what we're looking for. The final velocity is actually interesting. We'll talk about this in a second. And we know that the time in the air is 12 seconds. And we all want to know also how high it went. So this is actually something that I need you to think kind of logically about. We're dealing with a potato or an apple that shoots up and comes back down. And the big deal here is what's happening at the peak of its trip. And you can kind of think about this because you got to realize that first half of the trip takes 6 seconds, and the second half of the trip takes 6 seconds. And we actually know something. We know the velocity at the top. And that velocity, if we launch it from down here, is 0. And we know, if we launch it from down here, the final velocity up here is 0. But we have to remember that we're only talking about the first 6 seconds. So we don't really, we kind of care about the 6 seconds, but this, if we just look at this half of the trip, the going up part, we can figure out how high it goes because this will also tell us the height, okay, the height of this projectile. Knowing again that the velocity up top is 0, the acceleration is negative 10, but if we realize this, we're talking about only 6 seconds in the air as opposed to 12 seconds. So logically, you need to really think about the fact that, it spends 12 seconds in the air, but we really only need to look at half of the trip. So if we use the equation VI, or any equation with VI, VF, A, and T in it, I would say VF equals VI plus AT. And final velocity at the top is 0. VI is what we're going to look at, plus A, which is negative 10, times T, which is now 6 seconds. So 0 equals VI plus negative 60. We're going to have to add 60 to both sides and end up with 60 equals VI. So interestingly enough, we now have an initial velocity of 60 meters per second. And we can use this, if I shoot it up with 60 meters per second of velocity, we can figure out how high it goes, what that displacement's going to be. And we can do that with, I kind of like going with VF squared equals VI squared plus 2AD. You can probably use distance formula too, D equals VIT plus 1/2 AT squared. But I just find this convenient because the VF is 0. Equals VI squared, 60 squared is 3600, yeah, that sounds right, times 2 times, plus, not equals, plus 2 times negative 10 times our displacement. So what's next? We're going to have to subtract 3600 from both sides, equals negative 20D. And that's a good thing that we've got a negative 20 here and a negative 3600 here, so that means our D is actually going to be positive because it goes up. And 3600 divided by negative 20 is 180 meters. So there is how high it goes, and there is how fast it is going when it comes out. Next, Big Poppy, David Ortiz, hits a pop fly straight into the air, assuming it goes up 65 meters and back down 65 meters. How much time does the catcher have to get under the ball to make a catch? Another VI, VF, ATD, and we are dealing with projectiles, so the A is going to be negative 10 or negative 9.8. And we are trying to figure out time. Hits a pop fly straight into the air. We know it goes 65 meters. So we're looking for time, but we don't know the initial velocity, and we don't know the final velocity, sort of. We don't know the velocity that the batter hits it with, and we don't know the velocity that it would get caught with, but we do know that the velocity at the top, just like we did with the last problem, is 0. So if we look at half of the trip, we know a lot more than we think we do. And we can say, all right, let's look at the first half of the trip again. Make that final velocity 0 meters. Some stuff out. We need time. And there's no real equation that's got a VF, a T, and a D in it, but if we can figure out the initial velocity, then we're going to kind of have a better shot here. The other thing we can do is figure out, instead of going up, we can try and figure out some stuff coming down. And if it's coming down, we know the initial velocity at the top is going to be 0 meters per second. And we don't really care about what the final velocity is. All we need to know is that it drops. So again, if we look at it from just the top coming down, we don't care about the first time, we'll have the second time. And if you remember, one of the fundamental things about kinematics is when you launch something and catch something at the same height, the time going up equals the time coming down. So if we figure out the time coming down, we just multiply it by 2 to get the time going up and the time coming down. And there is an equation that we've got, VIATD, that would, really help us out. D equals VIT plus 1/2 AT squared. We know that D is 65. The initial velocity, if we look at it from the top, is 0, which makes things a lot easier for us, plus 1/2 times A, which is -10. So this is just going to become -5 T squared. So -10. So 65 equals -5 T squared. We're going to divide both sides by -5. And then we will end up with T squared equals, now here's the trick. This is 65 meters, and it goes 65 meters high, right? Well, we're looking at it from the top, and it's going to fall 65 meters, which means this is actually a -65 meters. Okay? Now, -65 divided by -5 is going to give us 13. Positive 13, which is really important because we're going to need to take the square root to get the time. Okay? And T, if you take the square root of 13, you end up with 3.6 seconds, which again is just the time coming down, but we need also the time coming back up. So what we're going to do is multiply that by 2 to get 7.2 seconds, which would be the whole trip time. Okay? Now, important, if you don't have a -65, if you don't make the realization that, okay, we're talking about coming down here, so the displacement from here down is going to be negative, you're going to end up with a -13, and you can't take the square root of that. So if you ever ended up in physics trying to take the square root of a negative number, you're missing a negative sign somewhere. So on the midterm, try and keep that in the back of your mind. All right, it's a big hint. And that's it. So we know how much time the catcher has to get under the ball. It's 7.2 seconds. Next one, a projectile experiences acceleration as it travels in the x horizontal dimension, assuming no additional force or air resistance. That is 100% false. A projectile experiences no acceleration. And if you remember, we had the little car, and the car, I don't know, it's going to be a terrible drawing, but here's the car, and there was the ball that went up, and the car kept moving, and the ball landed back in it. So while it was in the air, it didn't speed up or slow down, and we know that because the car didn't really change velocity, and the projectile, the ball, landed back in the car. Next one, a projectile experiences acceleration as it travels in the y dimension. Absolutely true. And we know that is technically -9.8 meters per second squared, which I always round up to -10 meters per second squared because it makes the math a little bit easier. Next, the acceleration on all objects is exerted, -9.8 or -10, whatever you feel like doing. All right, next, Grand Canyon. At its deepest point is 1,600 meters deep. If I were to drop a rock into this deep part of the canyon, how long would how long would it take to hit the bottom? And then how fast will it be going? This sounds like a VI, VF, ATD problem. If we're dropping it, the initial velocity is going to be 0. We want to know how fast it's going to be going, and we also want to know how much time it's going to take to hit the bottom. But because it's a projectile, we know that's -10 also. And we also know it's falling -1,600 meters, and that's really important. That negative there is going to make all this stuff work out for you. Okay? Remember, it's falling. So, An equation that we can use for this, I would say d equals VIT plus 1/2 AT squared, because I want to figure out the time. Okay, and you kind of look at this and you're like, oh, there's a t and a t squared, I have to use quadratic formula. You really don't, because the initial velocity here is 0. So negative 1600, if we start plugging some stuff in, equals 0 times t plus negative 5, 1/2, and negative 10 t squared. 0t is going to be 0. Negative 1600 equals negative 5t squared. Divide both sides by negative 5. Again, very important, if we have the negatives, they cancel out and become positives, and you end up with the square root of a positive number. 1600, the square root of 1600 divided by 5 is going to be 320, and then we take the square root of 320. T shall be 17.88 seconds. That's the first thing we want to know. And then the next thing we want to know is 7.88. The next thing we want to know is how fast is it going to be going when it hits the ground, or when it hits the Colorado River at the bottom of the Grand Canyon. I think the best equation to do that, now that we have time, is going to be VF equals VI plus A plus AT. And let's just plug and chug. We don't know the VF, but we do know the VI. We do know the acceleration, and we do know the time. And again, I love using negative 10 because it just means we move the decimal place over. So the final velocity is going to be 178.8 meters per second, with a big old negative there, because again, it is going down, and the negative means it's a vector, which means we're dealing with something going in the negative direction. Next up, on the paper it's number 10, but on this it's 1, whatever. If Michael Jordan has a vertical leap of 1.29 meters, what's his takeoff speed and his hang time? If you remember, hang time is the time up plus the time down, the total time he's in the air. Sounds to me like a job for VI, VF, ATD. Michael Jordan, once he jumps up, he is a projectile, which means A is going to be negative 10. And again, we're dealing with something going up and back down, and we know the height here is 1.29 meters, and he's jumping up. And we want to know his takeoff speed, and we know how fast he's going at the top after his 1.29 meters in the air. So we know his final velocity there is 0. He jumps up, slows down, stops, and then comes back down. We know whatever his initial velocity is enough to get him up there. So we can actually use just this information to figure out his initial velocity. Once we've got that, we can attack the time, because we'll also be able to figure out how long it took him to get up, and all we have to do is multiply that by 2 to figure out how long it gets him back down. So best equation for this, I think, if we're dealing with a VI, VF, and an A and a D, it's going to be VF squared equals VI squared plus 2AD. For those of you in Mr. T's class, I think your equation is VF squared equals VI squared in projectile motion plus 2GD. All I do is, I look at any acceleration, including gravity, as just an acceleration. So I just substitute in an acceleration negative 10 when it's gravity, and some other acceleration when it's a car or something else. So VF squared equals VI squared plus 2AD. Plug and chug. I don't know this. Plus 2 times negative 10 times 1.29. Now be very careful here. So many of my students are so used to looking at 1/2 of A, they're just going to, in their minds, make this negative 5, and that is not true. This is negative 20. VI squared plus negative 20 times 1.29. Negative 20 times 1.29 is going to be VI squared plus negative 25.8. And now we have to do some math. Add 25.8 to both sides. So we end up with positive 25.8 over here equals VI squared. And that's a good thing, because we need positive to be able to take a square root. VI is going to be 5.07 meters per second for the VI. So there's your VI. I call it 5. And then if we want to know the time, we can now go VF equals VI plus AT. And VF is still 0 at the top, but we now know our VI. I'll just call it 5 plus negative 10t. We're going to have to subtract 5 from both sides. So negative 5 equals negative 10. I can't write. Negative 10t. And negative 5 divided by negative 10 is going to be a time of, we'll call it about a half a second. Okay? But remember, that half a second is the time it takes him to go up, which means it takes him another half a second to go down, or the t total, the hang time, is actually going to be about 1.0 seconds. Okie dokie. So that's his hang time. He's in the air for a full second. I remember watching when I was your age Michael Jordan actually play, and yeah, he seemed like he was in the air for much more than a second, but really that's all he was in the air for. Next up, we are dealing with a plane having a takeoff speed of 88.3 meters per second, requires 1,365 meters to reach that speed. Determine the acceleration. So now we're not dealing with projectile. So we actually don't know what our acceleration is. But we have some other information here. It has takeoff speed. So how fast are you going when you start? The initial velocity of a plane trying to take off is usually 0. And we know it's going to get up to 88.3 meters per second. We're looking for the acceleration, and we're also looking for the time, evidently. And we know that this all happens over 1,365 meters. So we can do a little bit of math. I think we should probably start by getting the acceleration, because all of our time equations, anything with time also has acceleration in it. So I think we need to get the acceleration first. VI, VF, A, and D, I think the best equation to do this is going to be VF squared equals VI squared plus 2AD. 88.3 squared equals 0 squared plus 2 times A. Don't put negative 9.8 or negative 10 in there, because we don't know, it's not a projectile, so we don't know what that acceleration is, times D, which is 1,365. And let's see, 88.3 squared is going to be a ridiculously big number, 7796, equals 2 times 1365, that's going to be 2730 times A, and 0 squared is 0, and I just ignore it because it's 0. So now we're going to divide both sides by 2730, and we should get an acceleration of 2.85 meters per second squared. So now the question is, what's next? All right, we got acceleration 2.85, but now we need to figure out the time. And I think the best way to do that, VF equals VI plus AT. VF is 88.3 equals VI, which is 0, plus 2.85, because we just figured that out, times T. And we will end up with 2.85t equals 88.3, because 0 disappears. Divide both sides by 2.85. And time will be about 31 seconds, 30.98 seconds. And that's about right. If you've ever been on an airplane leaving Logan, it takes you about a half a minute to get from, being stationary at one end of the runway to actually flying to someplace warmer than it is here, because it was snowing this morning. Anyway, so I hope that makes sense. Go to the next one. Again, another problem that's not a projectile problem. VI, VF, ATD. A dragster accelerates to a speed of 112 meters per second over a distance of 398 meters. Determine the acceleration. Well, can't be much more straightforward than this. 398. Don't care. Acceleration is what we're looking for. Final velocity is 112, and the initial velocity is 0. Not 6, 0. So I'm going to say VI, VF, A, and D. The equation I want to use is VF squared equals VI squared plus 2AD. Again, you're looking for an equation that doesn't have a T in it, because we don't have it, and we don't ask about it, and we don't care about it. So 112 squared equals 0 squared plus 2 times a times 398. 112 squared equals whatever 398 times 2 is, which is 796 a, and 112 squared is 12544, if I can read my handwriting, times 796a. See, you think I'm doing this in my head? No, I did it like 5 minutes before I started the video. Anyway, and then divide both sides by 796. I wish I could do this in my head. 796, see that. A equals 15.75 meters per second. Okay, squared, meters per second squared. So there you go with your acceleration, and that's all we ask you. So that's pretty good. And we can go on to the next one. Ball is thrown 35 degrees above the horizontal at a speed of 35 meters per second, assuming no air resistance. Where will the ball land? This is no longer one-dimensional kinematics. This is two-dimensional. So we've got a ball, and it's going to be thrown, and it's going to land. And we are trying to figure out where that is. So the first thing we need to do is figure out what the velocity was that the ball was thrown in. And I do give you some information, but you have to be ingenuitive in what you do with it. We tell you that the ball is thrown 35 meters per second at an angle of 35 degrees above the horizontal. Ladies and gentlemen, we need to make a triangle. And we need to figure out what the velocity in the x is and what the velocity in the y is, because we can't do anything with diagonal lines in physics. But we can do things with straight lines in the x dimension and the y dimension. In order to get the x dimension, we're going to use cosine, the cosine function. So hypotenuse, I'm going to take the shortcut, 35 cosine 35. 35 times cosine of the angle will give you the adjacent side, and 35 hypotenuse times the sine of 35 will give you the opposite side of this triangle. And according to what I did, which if you look at my answer sheet, it's really small and hard to see, the adjacent side is 28.67 meters per second, and the opposite side is 20.07 meters per second. And now we can do some damage here. Now we can treat this like a real projectile problem with a VI, a VF, and an A, a T, and a D, but we have to remember something. We are no longer dealing with one dimension. We are dealing with two. One of those dimensions is the x, and one of those is dimensions in the y. And we have to remember a couple of things here. In the x dimension, there's no acceleration. Remember that true-false question we had a while ago? And in the y dimension of a projectile, we are dealing with negative 10 meters per second squared for acceleration. We also now know the initial velocities. In the y dimension, we're firing this thing up at 20.07 meters per second, and we're going to assume that it's going to come back to the same height that it launched with. This is how I sort of work these things. Unless otherwise told, they start and stop at the same height. So my displacement here is going to be 0 in the y, because it's going to the difference in height from start to finish, there isn't any, but there is difference in distance. And we also know that when you fire something up, it's going to come back down with the same velocity. So if I fire it up going positive 20.07, it will end coming down with negative 20.07. We also know the x dimension. We also know the x initial velocity of 28.67 meters per second. And if it doesn't speed up or slow down, it's going to come back with the same velocity. Okay, so it's never going to speed up or slow down in the x dimension. It will slow down and then speed up negatively in the y dimension. In order to figure out this, we need to know this. You can't figure out displacement without time. Every single displacement formula we've got that we can use in two-dimensional kinematic problem has time in it. Okay, so now it's just a matter of figuring out which equation we can use. A VI, a VF, an A, and a T, I say VF equals VI plus AT. That's a great formula to use. VF is going to be negative 20. I'm just going to round this down to 20 because carrying a 0.07 is foolish. Negative 20 equals 20 plus negative 10t. Subtract 20 from both sides. Negative 40 equals negative 10t. See how nice and easy using negative 10 is? Divide both sides by negative 10. I don't even need a calculator. My time is going to be 4 seconds. And that's the other reason I got rid of the 0.07. Technically, it's almost 4 seconds, but the physics is not what's going into a calculator. The physics is seeing what's going on here. So we know now 4 seconds is my time. There. Once I got my 4 seconds, now I can use another equation, which is an equation that we use in my class with things going in the x dimension. Because there's no acceleration, that equation is velocity equals displacement over time. We use this when there's no acceleration, and in the x dimension, there's no acceleration. So 28.67 equals displacement, which is what we're looking for, over time, which is 4 seconds. And if you multiply both sides by 4, you will get the displacement. 4 times 28.67 should give us a displacement in the x of, I had it and I lost it. Where did you go? 114.68 meters. 114.68 or something close to that. Anyway, if you end up with about 114, 115 meters on your paper, awesome. If you ended up with 300 meters, not awesome. So if you're in this zip code, you and I at least are on the same page. Okay? So again, when you see a launch problem, and I think we actually wrote down in the midterm, if it's a launch problem or a cliff problem, which we'll do next. But if it's a launch problem, first thing you got to do is, not graffiti your paper. First thing you want to do is figure out the x and y initial velocities, plug them into your chart, realize what the accelerations are, figure out your time, and then you can figure out your displacement. The next question is copy. Next question is about the Grand Canyon. So now this is going to be a cliff problem. Grand Canyon at its deepest point is 800 meters. If I were to drop a rock in this part of the canyon, how long would it take to hit the bottom? If I threw the same rock with an initial velocity in the horizontal direction, 20 meters per second, where's it going to land? So now, instead of something getting launched, we're talking about just dropping something straight down and launching something, or dropping something, well, not launching. We're talking about throwing something, sorry, with some x initial velocity. And we're going to end up with either a straight line going down or a parabola. That's a terrible parabola, but that's okay. So, one thing we know is the time to go straight down, or the time to go in this parabolic fashion, it's going to be the same time. So, we can start off with a chart, VI, VF, AT, D. And I'm actually going to try and answer both of these at the same time. The first part of the question deals strictly with the Y. All right, so we know that the Grand Canyon's 800 meters deep, so I'm going to fall 800 meters. I'm going to have an acceleration negative 10, and my initial velocity is 0. Okay, and I'm going to be able to figure out the time here, which is the same time as if I threw it off the cliff. Okay, so I'm actually going to draw a nice old box to say, hey, these are the same time. My initial velocity in the x, if I throw it, is 20 meters per second. And we know that there's no acceleration, so it will also end at 20 meters per second. I don't ask you about the final velocity. I could, and we could do some math to get that. But I think we've got a pretty good idea to see, all right, if we can use this stuff to get time, we're going to use the same time to get the displacement here, which is what we ask. Okay? So we need time and we need displacement, and they're going to be the same time. They're going to be gotten using the same time. VI, AT, D, I'm going to say D equals VIT plus 1/2 AT squared. And I love using this equation again because the initial velocity in the Y is 0. So I'm going to use all Y stuff in this equation. Negative 800 is my displacement in the Y. 0 is my initial velocity in the Y. Plus negative 5, that's for my acceleration in the Y. t squared. Again, 800 negative 5. If I can do the math in my head, I'm going to end up with 160 equals t squared. Okay, I love using negative 10 instead of negative 9.8, but that's me. And again, negative 5 and a negative 800, the 0 goes away. You're going to divide both sides by negative 5 to get 160. Once you got that, square root, t is going to equal, that I can't do in my head, 12.64 seconds. So now, I know it takes 12.64 seconds to fall down in the y, but it's also, I mean, remember that the rock is still going down the same distance, so it's going to take the same amount of time if we throw it off the cliff. So now again, I'm going to use that equation b equals d over t to figure out stuff in the x because there's no acceleration in the x. 20 equals displacement over time, which was 12.64, and we should end up with a distance of, if we do this right, 252 meters. Remember, cross multiplying 12.64 times 20 gives you 252-ish. Okay, so that's how far away it's going to land, and that's the answer to the displacement of the x. Cool. Next, easy question. What are the 4 fundamental forces of the universe? Remember that big long video that we made you watch and stuff? Gravity is one. Electromagnetic is the next. Strong nuclear is the third. And weak nuclear is the fourth. And if I were you, I would know what these 4 do. Gravity is all about why planets stick, why planets form and how stars make things, hold planets in orbits. Electromagnetism is why you don't fall through your chair. It's also why you end up with lightning causing disturbances in magnetic fields, so you get compasses that spin during lightning storms. It's also why chemistry happens. Strong nuclear is what holds the nucleus of an atom together. It holds the protons and neutrons together. And the weak nuclear is responsible for radiation if we change a proton into a neutron. Okie dokie. So those are 4 things to know. And we get into dynamics next. We're done with our kinematics, kind of. You'll see how in a second. Anyway, we got an applied force of 50 newtons used to accelerate an object to the right across a frictional surface. Believe it or not, this picture is what this text talks about. The object encounters 10 newtons of friction. 10 newtons of friction. Use the diagram to determine normal force, net force, mass, acceleration, neglect area resistance. All right. Well, first off, if it's on a surface and gravity is 80 newtons, then we know the normal force is also 80 newtons. Okay, gravity is technically negative 80 newtons, and the normal force is going to be positive 80 newtons. Second, if the gravity is negative 80 newtons, the mass is going to be 8 kilograms. Because remember, 8 times 10, or 9.8, if you use 9.8, you're going to end up with a little different than 8 kilograms. But because I use negative 10, 8 kilograms. 8 times 10 equals 80. Right? So in order to get the Fg, you multiply the mass times the pull of gravity. Okay? And this is sort of an aberration of Newton's second law. The acceleration is gotten by remembering that F net equals ma. Well, we can't get a without knowing what the F net is. If the normal force is 80 and the gravitational force is negative 80, the net force going in the y dimension is going to be 0. But we have an unbalanced force in the x dimension. We got 50 going to the right and 10 going to the left, which means F net, which is the sum of all forces, equals positive 50 plus negative 10, which is equal to positive 40. So the net force is 40 newtons, and if the net force equals ma, 40 equals the mass is 8 times a. We end up with 40 divided by 8, which if I remember my times tables, 8 times 5 is 40. My acceleration is 5 meters per second squared. I hope that made sense to you. It's a very simple free body diagram using Newton's second law to fill all this good stuff in. Next, we've got Newton's second law again, and we've actually got a mu, and we're going to have to figure out friction, so we're going to need to know some stuff. First off, 5 kilograms Fg is 5 times g, which is 50, negative. And if there's gravity going down, but it's not going through a floor, the floor has to be pushing it up with positive 50 newtons. And then we've got this friction thing. And if you remember, Ff equals mu times the normal force. And we know the mu is 0.1. It says so there, and it also says so in the diagram. I didn't even look at the words here. I'm just trying to fill in stuff. Mu is 0.1 times the normal force, which is 50. So 0.1 times 50 on a good day is 5 newtons. Ooh. And technically, it might be moving to the right, so we'd have to have a negative 5 because it's moving to the left. And now the net force, because up and down cancel out, there's nothing going to the right. The the frictional force is the net force. Okay, so if we know the frictional force and there's nothing counteracting it, the frictional force is the unbalanced force working on the object. So that's going to be negative 5 newtons for the net force, and negative 5 newtons equals the F net, which equals ma. But we know the mass because we figured that out, or I'm sorry, they told us, they, me, I, equals 5a. Negative 5 divided by 5 is going to be an acceleration of negative 1 meter per second squared. So, there you go. Hope that made some sense. Next. Brian is walking through the school cafeteria but does not realize the person in front of him just spilled his carton of chocolate milk. Oh no. As Brian, who weighs 420 newtons, steps in the milk, the coefficient of sliding friction between Brian and the floor suddenly drops to 0.04. What's the force of sliding friction between Brian and the floor? Ff equals mu Fn. We are looking for Ff. Mu is 0.04. Normal force. Brian weighs 420, so we got a 420 down, 420 newtons down. But he's on the floor, so he's not falling through, which means we have to have a normal force, that's gravity, of 420 newtons positive. So there's your normal force, 0.04 times normal force, which is 420 positive. We are going to have 0.04 times 420, which on a good day, and the correct sheet, equals 16.8 newtons. Fair? That shouldn't be that hard. Next question. While redecorating her apartment, Kitty slowly pushes an 82 kilogram china cabinet across the dining room floor, which was just sliding force of friction with 320 newtons. What's the coefficient of friction? Again, Ff equals mu times the normal force. The big deal is we have to figure out what the normal force is, which is basically equal to the opposite of gravity. So I've got this china cabinet getting pulled down with gravity. Fg equals mg, which is 82 times gravity, which is negative 10. So Fg is 820 kilograms, or I'm sorry, 820 newtons negative. And if it's not going through the floor, we've got a normal force of positive 820 newtons. So Ff, which we tell you is 320, equals mu times the normal force, 820. 320 divided by 820 is going to be a mu of 0.39. Next, Sky is trying to make her 70 kilogram St. Bernard go out the back door, but the dog refuses to walk. I hate when that happens. Coefficient of sliding friction between the dog and the floor is 0.5. How hard must Sky push in order to move the dog with a constant speed? With constant speed, there's no acceleration, so the push force equals the force of friction. Okay. Bad picture. Dog. Free body of dog. 70 kigs, so Fg must be negative 700 newtons. Normal force must be positive 700 newtons. We are trying to figure out how big Fp must be. If we're going to move it with a constant speed, the Fp to the right has to equal the Ff to the left. And the Ff equals mu Fn, Well, let's see if we have enough here to figure out what the friction is, because if we can figure out the friction, then we can figure out the push. Mu is 0.5. The normal force we just established is 700. So 0.5 times 700 is 350. If friction is 350 to the left, that's a negative 350 newtons, which means the push force must be positive 350 newtons. There, I hope so. Not hard. We're just trying to make you get used to using the frictional equation. Now these last three are great problems because they tie together dynamics and kinematics. And I really hope that this has been doing a good job recording, because I just don't want to write it again. All right, so a deer jumps out in front of my car as I'm traveling 25 meters per second. I jam on my brakes and lock them, and the mu between the tires and the ground is 3.6, which is a ridiculously big mu. Okay, remember mu maxes out at 4. So 3.6, this is like tires which have glue on them, and you know the road is dry and everything's all hunky-dory. If the mass of my car is 1,250 kilograms and there is the deer is 50 meters away from my car, will I or will I not hit the deer and have like nastiness on my hood? So first thing we need to figure out is what the acceleration is, because we're dealing with, all right, VI, VF, ATD, and ultimately we want to know what the displacement is. Okay, how, you know, the deer is 50 meters away, how far does it take me to stop? That's the ultimate question. I know I'm starting out at 25 meters per second, and I hope that I stop, so my final velocity is going to be 0. That is the dream, okay? In order to, I don't tell you the time, nor do I tell you the acceleration. So in order to figure out the displacement here, you need either the time or the acceleration. But we've been dealing with Newton's second law, which is F net equals ma, okay? Coincidentally, there's an A here and an A here. So if I can figure out what the acceleration is, I can figure out how far the distance is for me to stop. Remember also that the F net is the sum of all the forces, which means here's my car. I've got 1,250 kilogram car, which means the FG is 12,500 newtons, negative, and the normal force is also 12,500 newtons. Okay? And if I'm traveling along to the right, I jam on the brakes, which means I've got a force of friction to the left. So a free body diagram actually does really help. I know for a fact that the summation of forces in the y dimension are 0. Okay, these are going to add up to 0. So what really is the net force on my car is really the force of friction. And if I know the force of friction, well, that's ma. Okay? And if I can figure out the acceleration, I can plug it into here and then figure out how far it takes me to stop. So I hope you understand that when you're dealing with these situations, the net force is friction. Okay? That's the big deal. And force of friction equals mu times the normal force. And we tell you what mu is, 3.6. And we tell you, well, you get the normal force, 12,500. So 3.6 times 12,500 is a ridiculous amount of friction. Force of friction on this car is actually 450,000, nope, not 450,000 newtons, I'm sorry, 45,000 newtons. 45,000 newtons. And again, if we're traveling forward, the force of friction must be acting backwards, okay? Now, 4,500 newtons equals the force of friction, which is also the net force, which is equal to ma. But I know the mass. The mass of my car is 1,250 kilograms. You can tell I've been doing this for a while because I'm getting sleepy. 1250 kilograms. So 45,000 divided by 1250 gives me my acceleration. Okay? And we can figure out the acceleration by doing that division, remembering that it's a negative because the car is going one way and friction is going the opposite way. So it would be a negative acceleration. And that should give us negative 36 meters per second squared for an acceleration. So now I have an acceleration, negative 36 meters per second squared. Now I have a VI, a VF, an A, and I'm looking for a D. VF squared equals VI squared plus 2AD. VF squared is 0. VI squared is 25 squared plus 2 times negative 36 times D. 25 squared is 625 plus negative 72D. Subtract 625 from both sides. Divide both sides by 72 and this is kind of cool. You have a negative on one side and a negative on the other side, which means even though you're going with a negative acceleration, you're still moving positively. You know, you're getting closer to the deer, not further away from it. You should end up with a displacement of 8.68 meters. Now, why is this a big deal? How far away is the deer? 50 meters. How long does it take you to stop? 8.68 meters. Do you hit the deer? No. Okay? And again, this is the dynamics. Look, why stuff is moving. Your car jams on the brakes and makes you slow down. How do you move? Another 8.68 meters. That's the beauty of physics. Okay? So next, 2 more, and then it's football time. I love shuffleboard or curling. You might see curling on the final, I don't know. Shuffleboard is a sport where a puck is slid across the court and come to a stop in a bullseye, basically. The length from the release point to that 10-point value is 33 1/3 meters. So basically you have like a little shuffleboard thingy, and you make it go 33 1/3 meters away, and then there's like a score thing, and it's sort of weird hopscotch. I don't even remember. 10 points, and it's like 9 points, and then 8 points, and then you lose 10 points if you go too far. Anyway, mu is 0.3 for a 0.3 kilogram puck in the court. With what speed must the puck be pushed to land at the 10 points? So if I want to land it here, how hard do I have to push it? VI, VF, A, T, D. We are looking for the final velocity. We are looking for the initial velocity. We know the final velocity is 0 because we want the thing to stop there. We don't know the acceleration. We don't know, nor do we have access to the time, but we know the displacement is 33.3 meters. Now, I'm going to go a little faster than I went with the deer problem because this is basically the same thing. F net equals the force of friction, which equals mass times acceleration, and that's ultimately what we're looking for. The force of friction is mu times the normal force. Okay? And some of you may be getting a little ahead of us because you're realizing that the normal force is just m times g, which equals ma. And the masses can cancel. But if that doesn't make sense to you, don't worry about it because we'll do it the old-fashioned way. But after the mid-year, we're going to start trying to give you some of these little tricks. So mu times the normal force is mu, which is 0.3, times the normal force, which is 0.3 kilograms, times 10. So 0.3 times 10 is 3, times mu of 0.3 gives us a force of friction of 0.3 times 3, 0.9 newtons. So far, so good. So mu times mass times gravity, which gives you the normal force. And that will eventually give you the frictional force. So now I know friction is 0.9 newtons. 0.9 newtons equals ma. but the mass is 0.3, so 0.9 divided by 0.3 gives us an acceleration of 3 meters per second squared. So far so good? I hope so. Now, if the puck is going to the right, friction must be pointing to the left, so it's actually a negative 3 meters per second squared. Negative 3. And this is all fine and good. We can move this there, which we just did. And now I got a VI, VF, an A, and a D. Again, VF squared equals VI squared plus 2AD. 0 equals VI squared plus 2 times negative 3 times 33 1/3. Okay, let's see. 0 equals negative, let's see, 33.3 times 6. VI squared plus negative 199.8. We have to add 199.8 to both sides. And then we can take the square root. And we should end up with a VI of 14.1 meters per second. Okay, so that means in order for me to hit it at the I shouldn't point at my computer screen, you can't see that. In order for me to hit at the, in order to have the puck stop at the 10-point spot, I have to push it back here with initial velocity of 14.1 meters per second. Any faster, it'll go too far. Any slower, it won't go far enough. So again, dynamics leading to kinematics. And finally, the last question after like an hour. What's the final velocity of a bowling ball that has a mass of 7 kilograms after it's traveled 30 meters down a bowling alley? Starting with initial velocity of 17 meters per second, and the mu is 0.03. VI, VF, A, T, D, we know some stuff. D is 30 meters. Don't know about time, don't ask about time. Acceleration we have to figure out. Final velocity is what we are looking for. Initial velocity is 17 meters per second. Okay, F net equals the force of friction equals ma. Okay, and the reason, and we haven't figured it out yet, you got normal force and gravity, so Fn, Fg, and once you release that ball, there's only one force left on it going horizontally because you're not pushing it anymore. That would be the force of friction. So once we know the force of gravity, which is 70, negative, the force normal is positive 70 because it's a 7 kilogram thing. Force of friction equals mu times 70. And mu is 0.03. So FF equals 0.03 times 70, which equals MA. 0.03 times 70 is 2.1 newtons, which equals MA. But we know the mass, and that is 7. And we also know that this is a slowing down force, so it's going to become negative because the bowling ball is moving to the right, the acceleration is to the left. So the acceleration on the bowling ball is going to be negative 0.3 meters per second squared, because negative 2.1 divided by 7 is 0.3. So my acceleration is now negative 0.3. And again, VF squared equals VI squared plus 2AD. VF squared is what we're looking for, equals VI squared, which is 17 squared, plus 2 times negative 0.3 times 30 meters is going to be something. So 17 squared plus 2 times negative 0.3 times 30 is going to be 271, equals VF squared, square root, and this is a big deal. 17 squared is a bigger number than 271 because we're adding a negative number here. Just keep that in mind, okay? Square root of both sides is 16.46. Yeah, And remember, this is, I guess, the big logic question. Look, if you throw a bowling ball, if you roll a bowling ball and there's friction and you started at 17 meters per second, you should end up with a final velocity that's less than 17 meters per second. Okay, so on the midterm, if we ask you a question like this, be sure that you pay attention to this, which is a negative, okay, which means it's 17 squared plus a negative something or other, okay? So that's it. I hope this helped. This is the last question on the review sheet for my class. I'm actually going to try and scan these in so you can see my work, although I did it on this, but and it's a lot more scrunched up on my stuff. And if you're in Mr. T's class, I hope this made a little bit of sense. And good luck with your studying, and go Pats.